This is the brief on partial differential equations, or PDEs. We've sifted through 16 sources to get to the core mathematical rules that govern physical systems. You know, everything from waves and heat transfer to structural stability. And it all really boils down to three essential principles. First up, boundary conditions. These are what fundamentally dictate the result. You can think of them as the absolute non-negotiable rules of the game. So for heat transfer, an insulated edge, that's called a Neumann condition, means no heat escapes. You're going to end up with a high uniform temperature. But switch to a fixed temperature on that edge, a Dirichlet condition, and now you're forcing a steep gradient and getting maximum heat flow. See? The boundary changes everything. Second, equilibrium is all about finding the minimum energy state. The system is always trying to find the configuration that requires the least possible energy to maintain. For time-dependent systems, it's that initial high-energy gradient that really drives everything toward a flatter, more stable equilibrium. And finally, complex motions are built using superposition. A wild shape, like a plucked guitar string, is actually just the sum of many simple, independent waves all added up. The more detailed you want that final shape to be, the more of those high-frequency waves you have to pile on. Ultimately, every stable physical outcome is a function of its specific constraints, its lowest energy state, and the underlying math of its governing equation.